Okay, we're going to get started with our presentation here on advanced collision problems. Let me get into presentation mode here. This type of problem has come up on the AP exam in the past, and it's been a while. So this could be a problem that comes up because, they try to mix things up a little bit, and this one I haven't seen in a while. Anyway, so basically we're going to deal with these problems where you have linear motion and then things that can rotate, and then eventually we'll get to like a second case where things are going to translate as well. So first case we're going to talk about is that the stick is pinned, meaning that there's some kind of nail in here where once there's this collision, this thing is free to rotate. So there's some big ideas here, whether angular and linear momentum are conserved. So this is the big conceptual idea. Is angular momentum conserved? Yes, if the rod is free to rotate, i.e. there's no friction involved, angular momentum is conserved. So this is going to be our go-to to solve for things, conservation of angular momentum, whenever the stick has a pin in it or the rod has a pin in it. We also need to be aware that linear momentum is not always conserved, and that's why I have a no for the most part, because it turns out that there's a force from the nail on the board or on the stick that can cause an increase or a decrease in the linear momentum. So this is in your notes, and I think you can kind of read through it. But basically what we're talking about is an action-reaction force pair. So the stick hits, or the stick hits the nail pushes back on the stick. So if you hit on the end of the stick, the result is going to be an increase in linear momentum. If you hit closer to your pivot point here, there'll be a decrease in linear momentum. And the tennis racket is here just to kind of make a connection to maybe your experiences if you're a tennis player or a baseball player. But there does exist this sweet spot or percussion point where there'll be no force. And in this only case is linear momentum conserved. So you have to be mindful that typically what we're going to be dealing with is these two cases because they're more likely. All right, so how do we calculate linear momentum for something that's rotating about a fixed axis? Well, the initial linear momentum is probably not an issue at all to kind of consider. I have a list of all the givens that we're going to use in your notes here. The initial angular velocity, the mass of the stick we're going to use is going to be big M, and it's going to have a length L, and we can go kind of use those to get started. So if we want to determine the linear momentum of a rotating object, you're going to use the center of mass of the rotating object and use that the velocity of the center of mass is equal to r times the angular velocity. So if we know that angular momentum is conserved, we can solve for this final angular velocity, and this r would represent the distance from the pivot point to the center of mass. So I'll take you through three basic examples that we could see. So first one in your notes is a collide and stick. So this puck or disc comes, hits the stick, and the stick is free to rotate. Think of this as we're looking at it at like a top-down view, and the stick is on top of like an air table. So there's no friction that causes the stick to slow down. So again, it's free to move is what they say. So the final momentum of the disc, again, we're looking at the linear momentum of the disc, is going to be the mass of the disc times its final velocity of that disc. And if we think of it as collide and stick, that's the tangential velocity there. And then the final linear momentum of the stick is going to be the mass of the stick. And again, as I mentioned before, it'll be the velocity of the center of mass of the stick. So how do we calculate the velocity, that final velocities? We're going to use our non-slip condition, so r omega. So all we need to solve for here is the final angular velocity of the stick-ball combination. And again, recognize the stick is at the end, so that distance to the pivot point is L, and the distance to the center of mass is going to be L over 2. And we will use conservation of angular momentum to determine the final velocity. And I've set up the conservation of angular momentum equation down here, so take a look at it, make sure that makes sense. This is the total inertia of the stick pivoted about its end, plus the disc, and then this is the initial angular momentum of the disc as it approaches relative to that pivot point. Okay, so that's collide and stick. The second example is collide and bounce. These ones are definitely more challenging because it's going to hit. This is going to begin to angular rotate, and then this one will have angular momentum going backwards. We have to be careful of the signs. So if we treat this as having an initial positive angular momentum relative to the stick here, and that this is positive angular momentum, then this one, of course, would have to be a negative angular momentum. All right, so you have the final velocity stick. Again, setting up the same. Be careful of the signs. Again, I'm just kind of going through how to solve them, not so much example problems. And then you'd have to find that final velocity using that final angular velocity. Again, we're using conservation of angular momentum. Big idea, if there's a nail or a pin and it's free to rotate, only angular momentum is conserved. You would probably need some kind of value for this in order to set up the conservation of angular momentum equation. So you can see I have it set up here. Again, the same initial angular momentum. You have L times the final velocity here. I think that would have to be given, or maybe this would have to be given, one of those terms. But again, angular momentum is conserved. All right, next one. All right, colliding disk stops. So again, this one's probably a little bit more simple. Same idea how we're setting it up. The velocity of the center mass of the stick is going to be L over 2. And again, we'd use conservation of angular momentum to find the final velocity. And I think this next part is it okay? There's the initial angular momentum. You have the rod and its final. So I think that's okay. Yeah, I thought I had a typo in there, but it looks okay. All right, so that's colliding the disk stops. So if you go on to the example problem that's on the very last page, here are the answers to them. I will probably put up a solution, again, a screencast solution to this if you want to look. But again, I would try your hand at this. You're now partially able, I think, to finish up the web assign part. I just have to go through one more problem, and that's when there isn't a nail in the stick. So the disc hits a stick that's not pinned. There's no hinge. Is angular momentum conserved? Yes, same as before. Linear momentum is conserved. How is the rod going to move? It's going to translate and rotate about the center of mass. This is a link to a YouTube video that I think is, I will put the, I'll post this PowerPoint as well as the link to the YouTube video in your document. It's about a minute in, and it really gives a nice sense of what's going to happen. So this thing is going to hit here. The velocity of the center of mass is going to translate and then rotate about its center of mass. And this video really explains it both really nicely, so you can really wrap your head on. So you definitely need to watch this video, or at least it's about a minute in, so just a bit of it. So unless the collision is said to be elastic, kinetic energy is going to be lost. So we treat all of these collisions as as inelastic collisions, and you'd have to make sure that you consider both the rotational and the translational kinetic energies. So I think that's it. And so I think that's enough to finish up your web assign and practice that. I will post some more videos that you can work with. And again, thank you guys for being patient and working with me.